Welcome everybody, and thanks for joining our webinar. In today's webinar, we want to show you how CAESES can be used as a front end or GUI for OpenFOAM. And the presenters of today's webinar will be my colleague Carsten Fütterer and myself, Matthias Brenner. Carsten is a member of our pre-sales and support team. He has been with Friendship Systems for about 3 years now. He has a background in chemical and process engineering, and he is our resident expert for StarCCM and OpenFOAM. Myself, I'm currently head of sales for Europe here at Friendship Systems. I have previously also worked in our pre-sales and engineering team. I've been with Friendship Systems for approximately 8 years now, and my own background is naval architecture. In terms of the agenda for today's webinar, I will start by giving a short overview of CAESES, explaining what CAESES is and what it can do. Then Carsten will take over and show you a case example of a simple 90-degree bent duct. First of all, he will explain shortly how the parametric model of this geometry is built up and how it can be varied. Then he will show the pre-processing or geometry preparation steps that are necessary to make the geometry ready to be used by OpenFOAM. And finally show how to connect CAESES to OpenFOAM so that the OpenFOAM computation can be started from within CAESES. Once the computation is done, he will show how to do a little bit of post-processing of the results. And then he will show how to set up and carry out an automated variation of the geometry, starting an OpenFOAM computation for every variant that is created, and show how to assess the results that have been obtained by this design study. And finally, I will take over again with a short summary and some conclusions of the things we have seen. So for the ones of you that are not familiar to CAESES, let me come to a short introduction. CAESES is a so-called upfront CAE system, so it's meant to be used early in the design process for the simulation-driven design of any type of shape that is complex in nature and exposed to a flow. The aim of CAESES is to carry out design explorations and formal optimization and provide all the necessary tools within an automated process and within a single user interface. The advantages that can be obtained by using CAESES in terms of the design are, first of all, obviously that we would like to improve the performance of the design, but also we want to explore new concepts or custom tailor a certain geometry to a specific application. Another point is that by carrying out these design studies early in the design process, we can gain a very deep insight into the product behavior, meaning how the performance of the design changes by changing certain parameters of the geometry. In terms of the process, the advantages that can be obtained by using CAESES are that we can obtain a higher throughput in our design process because things are being automated and sped up, so that it's possible to analyze more geometry variants in a shorter time. And another point that is also sometimes important is that the CAESES is meant to be a tool for the simulation engineers so that they are able to generate and vary the geometries by themselves without having to rely on a CAD department to provide the geometry files. This next slide shows in a very simple overview the capability of CAESES. So the main module so to say, of CAESES is the upfront CAD. So we have a full CAD modeling package that can provide simulation-ready geometry and vary it in a very highly automated way, as well as preparing this geometry so that it can be used by the external tools that we want to couple to CAESES, which is also the next step in the process, the connection to external software. So CAESES is typically used with CFD simulation software, but it can also be any kind of other external software. And if we couple to CFD, then the external tool will take care of the mesh generation and the flow solving. In our examples today, this tool is OpenFOAM with its related mesh generators, Snappy Hex Mesh or Block Mesh. And finally, to automate the process, we have our optimization module in CAESES, which provides algorithms and all the necessary tools to carry out automated design explorations and formal optimization. So extraction of the relevant results, post-processing, controlling the optimization process, and finally analyze the data that has been created in the exploration or optimization. CAESES is, as I said, used typically in all areas where we have geometries that are complex in shape and that are in somehow relationship with a flow. So in this slide, you can see some typical examples. There could be, for example, ship hulls or powertrain components like piston bowls or intake, exhaust ports, manifolds, things like that. Another area of focus of CAESES is turbo machinery. So for example, we have turbochargers where we can work on the impeller as well as on the volute geometries. Propellers are another example for turbo machinery or any kind of turbines, pumps, but also industrial machinery applications like valves and other things. So let's take a look at how to use OpenFOAM and how CAESES can be used with OpenFOAM. So first of all, if we take a look at using OpenFOAM Standalone, then I think all of you know well that it is mainly a tool that can be used effectively by expert users that have the ability to write the dictionary files or adapt the dictionary files by themselves for a specific computation case. It's not very suitable to be used when some kind of automated geometry variation is involved. And in order to be able to carry out the simulation, it is necessary to have some kind of clean or prepared geometry. So if we talk about graphical user interfaces for OpenFOAM, there is different kinds. And here I have as an example Helix, which I think is a popular user interface for OpenFOAM. It has also a free version available, but is mainly, let's say, a placeholder for other GUIs that have a similar approach. The idea here is that it can be used for all user levels, so from beginners to experts. It's very suitable to set up a computation case from scratch in a very easy way. So the complete configuration of the case can be entered in the user interface, and the dictionary files are created automatically. It's very fast in setting up a case from scratch, but it is also not necessarily suitable to be used in the context of an automated geometry variation. With CAESES, the approach is slightly different than these other type of GUIs. CAESES is a tool that can be used, let's say, by mid to high level users. It makes use of existing dictionary files. So the purpose is not to set up the case from scratch, but we take the dictionary files that have been set up by the user beforehand, or maybe in a tool like Helix, as I mentioned. And we are able to modify entries in these dictionary files within CAESES in an automated way, which we will see later on in Carsten's part of the presentation. And CAESES is meant to be used together with OpenFOAM to carry out design studies or optimization where the geometry is varied and we want to trigger the computation automatically for all the designs that are being created. CAESES also can also be used as a geometry preprocessor in order to clean up the geometry and make it ready for the computation. So much from my side as a very short introduction, theoretical introduction to CAESES, and now Carsten will take over and show you in practice how using CAESES together with OpenFOAM looks like.
So thank you, Mattia, for this nice introduction. So I hope you can see now my screen. And I will guide you through the process of coupling CAESES with OpenFOAM on the example of this 90-degree band, which we already created in the last webinar. So if you have any questions how to create basically this geometry model, you can go to our website and have a look into this recording. So you can see this is a really simple example of a sweep duct. So it's basically an ellipse which is swept along a path here, and it's parameterized by several actual functions. For example, I can change the radius, the area of the path, which changes the curvature in this band. I can change the radius at several positions along the path. So for example, I can make it smaller, I can make it bigger, and so on. And I can also change the radius factor, for example, to 0.2. You can see it's more squeezed now. It's like an ellipse now in the middle. So it's pretty simple geometry, but now we want to prepare this geometry to use it in OpenFOAM, and the goal is that we export a colored STL, which has several patches for inlet, outlet, and wall, and we have to make sure that's watertight. So how we would do this here in CAESES, first step would be to create this outlet boundary. Therefore, I create an BWrap and use the operation faces from planar curves. So it basically takes the curves of the duct and creates this face. It's additionally colored with purple. So the next step in the process would be to create the whole domain. So therefore I create this BWrap here called domain. I have several options here, so operations here. So first thing is to add the source of the duct here and give it a specific color. Then I add the outlet boundary, and now I want to extrude the inlet so that I get a developed, more or less developed flow profile at the beginning of the bend. So by extruding this, I can also close this extrusion. When we go here, I can show you close extrusion and give this closure a specific color. Here in this case, light pink. So now we created this closed domain. Now I want to make sure that this geometry is really watertight. So I create tri-mesh from this. It looks like this. you can see it is watertight because it has no wet edges, which you would see. But what you could also see is the tessellation of the STL. So that's what you see here. This tessellation is basically what you would export for the STL. And you can see, yeah, it's not really nice. It has really coarse triangles here and really long, skewed triangles here. And this can really make, for example, snappy hex mesh, making a really hard job of meshing this geometry. So I want to change this tessellation. Therefore, I go back to my BREP, and in display options, I have several options. For example, I could decrease the angle tolerance so that it gets more, the curvature is much more captured, but I still have here this long triangles, and to get rid of this, I specify the maximum triangle length. For example, I could use some value like this, and now you can see we have a really nice looking tessellation of this duct, and OpenFOAM and Snappy Hex Mesh will like this tessellation. So that is basically how we would prepare our geometry. One more thing I will do here is to create a bounding box within CAESES. So I wrote a feature here in CAESES which creates this bounding box. It basically automatically calculates the maximum and minimum positions of my STL. So this is really nice because then your bounding box will always adapt to your changing geometry. For example, when I increase the radius in the middle, go here, increase the radius, also the bounding box will change. And I'm always making sure that my geometry lies within my bounding box. Okay, and I will also want to make sure that I set up a reference point. So this will later be used in OpenFOAM, so that Snappy Hex Mesh knows where the internal point is, where to mesh. And I created this point here along the path of the geometry. So with that, I really made sure that this point is always within the geometry. So inside this bounding box feature, I could specify an offset from the minimum and maximum positions. For example, I could increase this offset here, pretty easy, and I can vary the number of subdivisions of this bounding box here. For example, like this would give me a reasonable subdivision. And now I want to make some scaling of this mesh so that I can easily make a mesh study. So I introduce here a design variable called mesh scaling and use this. So I multiply each of this factor with this mesh scaling design variable. And now I could really easily make mesh study in an automatic way. So this is a really nice thing. So, and this feature here, the output is basically these two strings here at the bottom. So it basically creates a string for my bounding box, for my blocks, and for my reference point. And I will use these strings later in my OpenFOAM dictionaries. So that's basically it for the preparation of the geometry and the bounding box. Now I can start with actually the connection to OpenFOAM. So therefore I go to connections and we create a so-called software connector. You can see here the software connector consists of 4 windows. The first window is where we put in the geometry and specify the export type. The upper right window we put in the OpenFOAM dictionary files, and the both lower windows are used to read in the results from OpenFOAM. And this runner window here is used to specify the executable and the execute. Yeah. So now to start, the first thing what we do is just drag and drop easily our tri-mesh into the geometry window here, and we have to specify a name. So we call it sduct.stl. So that's the name which will be exported in each variant. But now I also want to make that it's exported in a subfolder. So I just write constant / try surface / sduct.stl. So this makes sure that this STL is always exported in the subfolder. Now I set up the export type. It's basically a multi-body STL. So this multi-body STL creates a patch for each different color of my tri-mesh. So again, go back here, it will create a patch for inlet, outlet, and the wall. So that's basically it for the input geometry. Now we want to set up our input files. Therefore, we use all my prepared OpenFOAM files without any. You may have to make sure that you don't read in some result values. So we just need these files which are used to run the computation. So, and also it is really convenient to use this convert to template option here. This basically will make sure that these files here and the are copied into the CAESES project. So add these files, and then you can see here are all these files, and they are copied into the project without any reference to the original file. So you could go into each file and write different things here. Yeah, here you can see I have set up all-run script here in this case. This all-run script basically will trigger each of my OpenFOAM utilities. And you can also use, for example, GNU-plot afterwards in this script to read in the, to create plots of your residuals or something like that. So now I want to modify my block mesh dict. So go double click on it, and you can see here like these vertices are fixed for the corners of the bounding box. So I want to replace these by my script. So I right click and create a new entry. So you can see now here's a new entry. I call this entry bounding box, and the type should be an F string, because I export from my feature and string. So I put in here the string for my feature bound box and press play. So I can evaluate this, and then you can see a little bit of the content here, how the string looks like. And I now also want to replace this line here for the grading and the subdivision of the block. Make a new entry, call this entry blocks. Use this type as string type. And also use the string from my feature. So that's basically it. So then my block mesh dict will automatically adjust to my changing geometry. Another thing I have to do is to make sure that the reference point, so the location in mesh of my snappy hex mesh, is always changing with my geometry, so that I can make sure that I'm always meshing inside the duct. So I make a new entry for this. Right click on it, location in mesh. It's a good name, but I change the type also to string and use my entry of my feature. So that's basically it to modify our mesh geometry. Now we could also introduce parameters, for example, for my iteration number. So I would go here in my control dict, go to end time and make a new entry, call this entry iterations, and also use this entry for my write intervals. So I select this, and now not new entry, but I use the existing entries, so I use iterations. So now you have here an iteration number. You could also create a parameter by right click, and then you can see you have a parameter for your iterations inside your cat tree. So you can easily change this now to 200. It's enough for showing things. You could also create entries, for example, for the inlet velocity, and new entry 0.5 meter per second. That's good. Maybe when I'm just here, you can see these different patches here. S dark purple, S dark gray. So all my patches are named with my colors, basically, which I set up to my VREPs. Yeah. So that's basically it to prepare my input files. Now I want to specify my result files. Therefore I will load my case.foam. So this is basically just a placeholder where cases looked if this file is in the design directory, it will read in the OpenFOAM VTK files so that we are able to post-process the results. So in this window here, result values, I want to read in my pressure drop, and just click to plus and add my file which I created. So double click on this, you will see the input of this file, and now I want to specify that this value here, my pressure drop, is a parameter in cases. So therefore I click the plus button here, call this P inlet. Now I have to specify the line. In this case, go through the line and specify the column. And now I have this P inlet value here, and from this I can create a parameter. And now I have a parameter for my pressure. And each time I want to update this pressure here, so it's not evaluated now, it will trigger my computation. So I put this into my solver directory. So, and that's basically it for here. Now I have to specify my executable, go to runner and create a new local application. So call this local application OF for OpenFOAM, but I'm using CAESES or OpenFOAM on Windows, so I specify my Cygwin executable, and I have to set up some arguments. Here you can see it will call this all run script here, which is here in my input files, this script. So when you are using OpenFOAM on a Linux machine, it would be much more easier. So you would just write here as an executable your all run script, this name here, and don't use any arguments. So that's even simpler on a real Linux machine. But now we are using Windows, and that's why we are using this. So now we actually did the complete setup for coupling OpenFOAM with CAESES, and I can actually run my computation. Therefore, I just click this one computation button. So then I can go to the tasks monitor and see the output of my computation, and you can see here the error, the output which you would also see in your terminal. So it's running now for 200 iterations. And then it reads in the results. So now it's finished. Now it's reading the results. And you can see now here in my table viewer, it reads in the pressure inlet value, which it just calculated. So I can also go here to my pressure inlet, and I want basically to multiply this by my density of the fluid, because it's water and the pressure calculation is normalized. So, and now I want to basically start the post-processing, or to show you the post-processing. Therefore, I go to connections, computations and results, to my runner, and now you can see I have this internal mesh here. So these are basically my OpenFOAM results, or VTK results. So now I have to create a new visualization, create new, and I want to create a grid plane cut. So that's always the first thing what you would do, and create a new contour plot, and then you can see the first results. So I want to specify my velocity here, and now you can see the results here. So now I want set of this lighting here and create a new color map. So then you can specify the color map a bit more. You can give it maybe 20 subdivisions, and you can also choose between different color maps. You can use continuous colors, and now I would use, I like this color map here. I could also switch between change the line coloring here. Yeah, and we could also create, besides the contour plot, for example, a mesh visualization to show if my volume mesh is clean, and you can really do a nice automation and see if your boundary mesh, for example, works for different geometries. So you could also create, when you go here, you could also create, for example, streamlines, vector plots, isosurfaces, and so on. But what I want now to show is using this probe surface here. With that, I can visualize all volume informations or scalar informations on any surface in CAESES. So therefore, I prepared a surface called probe surface. You can see it here. I switch off the bounding box. I want to visualize now the data on the surface here. So therefore, I use this probe surface, hide this, and I want to use a contour plot to show the results on this surface. Takes a little bit for the computation. And now you can see the results on this contour plot. So this is really a really nice thing in what you can do in CAESES for the post-processing. And you could imagine when you, for example, also run like a turbocharger, and then you create some meridianal surfaces where you want to visualize your input or your OpenFOAM results. Just a little example which you could do here. Now we are pretty much done. So all the connection is ready. We can read in the results. We can read result values, for example, the pressure drop. And now we can start an automated design exploration. And therefore, we would go to optimization. I want now to create a little SOBOL. This is a design of experiment. Go to SOBOL. Maybe I call it DOE. Yeah, using like 10 variants. Now you can specify your design variables. I want my design variable area go from 0.7 to 0.9, and maybe also my radius, which goes from lower bound 0.2 to upper bound 0.5, for example. And now, which is really important, I have to, for the evaluation, I have to specify my parameter for a pressure drop. So this eval P inlet. I select this. So this will trigger with each different design. It will trigger the OpenFOAM computation because it has to be updated here. Now we can also set up screenshots. Therefore, we go to this plus button and say 3D view screenshot. Having a preview, it would look like this. This is nice. Maybe I use this view here. Recapture and okay, like this. But now I also want to have another screenshot, for example, which includes my mesh visualization, for example, like this. And I'll go to my design engine, create a new screenshot, window here, preview, and then you can see you create a new picture with the mesh, and the old screenshot is also used. So now you are creating 2 screenshots with each design. And now you are pretty much done. And now it's really easy. Just press this play button here, and then all the variants are created. So press this play button here. Then a table is opened, and you can see different designs are created. And when I go back to my task monitor, I could also see the running designs. Now it's a little bit heavy computation here. That's why I also created a second case where the complete computation is already done. So these were my are my results from this computation. You can see here are different pressure drops. You can sort the designs with the pressure drop, and yeah, you can use charts to see the influence of each design variable on a parameter, for example. This is really nice when you want to get rid of some design variables, and then you can see which design variables have an influence on the pressure drop, for example. And I also have a design viewer. This is really nice to compare different designs. So you can see here are the screenshots for all my 10 designs. And you can go in and compare each different designs with each other. And here at the bottom, which is also very nice, you have a small 3D view. So you can basically rotate all of these geometries and see if the changes in compare the changes in specific areas, for example. So this is also really nice. And yeah, another possibility of comparing designs would be comparing my baseline design here with some of the designs which I just created. So therefore I would use this log results view, and I would jump into one of my designs. You can see here these are all my designs which I calculated, and 0, 0, 0 was my best design. And now you have this bar here, and you can blend between both designs, which is really nice. But you could also, for example, put the baseline here to the top, and then you can jump through different designs and compare each design with my baseline. So this is basically what I wanted to show you here in CAESES. Yeah, that's why I give you back to Mattia, and I hope you enjoyed this my part.
Thank you very much, Carsten, for this very interesting demonstration. Now I would like to wrap up our webinar by giving a short summary of the things we've seen and some conclusions. So if we look at what are the advantages of using CAESES together with OpenFOAM, then first of all, we can see that we have a full CAD tool available that we can use to model geometry, process geometry, and so on. We have the ability to carry out automated geometry variation in connection with the CFD. So every design that we create, as we have seen in Carsten's demonstration, will be automatically evaluated by OpenFOAM. We also have the ability of coupling our dictionary files to changes in the geometry. So Carsten showed a little bit of that in this bounding box he created for the block mesh dictionary, where he entered certain strings into the dictionary files that are updated every time the OpenFOAM computation is started, so that whenever some changes to the dictionaries are necessary due to the changing geometry, we can take care of that in an automated way. Apart from generating the geometry in CAESES, we have several different tools available for the pre-processing of the geometry. So we can tessellate an existing surface or BREP geometry. We can heal a geometry model. So what this means is that if we have certain gaps in the geometry or overlap, we can make sure that the geometry is clean, watertight. Additionally, we can also subdivide the geometry into patches that we can later use to assign different boundary conditions or different mesh settings. So we've seen this in the demonstration that we can assign different colors to the parts of the geometry, and then when we're using a multi-body STL export, which is supported by OpenFOAM, then we will get separate patches in our STL file. Another great thing when using CAESES is that we can not only connect to OpenFOAM, but we can connect all kinds of tools in a very similar way using the software connector. So we can create complete tool chains. So for example, Carsten mentioned using GNUplot after the OpenFOAM computation to generate certain graphs, or we can involve another grid, third-party grid generator like GridPro or Pointwise to generate the grid for the OpenFOAM computation. Another thing that is connected to our geometry variation is that we are able to compare results of different geometry variants to each other in a very easy way, either with the design viewer, where we get an overview of many different designs at the same time, or by using the direct side-by-side comparison of two designs, or we want to compare the baseline to all the subsequent designs that have been created. Another thing that we didn't touch on so much during the demonstration is the simulation data management. So CAESES takes care of organizing all the data that you're generating with your OpenFOAM computations on your hard drive. So it will create a folder structure where you store the data for all the different designs that have been created in a neat, so to say, way, and it's very easy to find the relevant data for certain designs. So finally, just a few notes that I would like to give you here along the way. Many of you might already be aware of that. There is a free version of CAESES aside our full commercial version, and the free version includes all geometry modeling and software connection capabilities, but it does not allow for automated optimization. In order to get help and get started with CAESES, and specifically with the free version, we have a community forum that you can take a look at. You will find a lot of different examples, tips and tricks, and of course you will be able to get help if you need it in the forum. And also Carsten told me that he will post the example that he showed in the webinar as a project file in the forum. So if you would like to take a look at the real project file that he has been showing, then go to the forum later on and you will find it there. Another nice thing which we have just launched very recently in order to help you get started with CAESES or CAESES Free is a series of tutorial videos that you will find on our website. Of course, there is also written tutorials that come along with the software if you download it. So with the help of these different things and also the forum, it should be easy to have a good start using CAESES. Finally, I wanted to point out two things. If you would like to follow more or get more information about CAESES, we have a blog where we post interesting projects and tips and tricks. So that's something that is nice to follow. And also, please take a look in our event section on the website, where we will post all the upcoming events, including webinars as today's webinar. And the next webinar in April, the exact date is not fixed yet, but in that webinar, we will show you a bit more in detail how you can pre-process the geometry, tessellate it, make it watertight in order to use it for your grid generator or with OpenFOAM, as was shown here. So finally, thank you again for joining our webinar. I hope to see you again in one of our upcoming webinars or to be in touch in any other way. Just a small note, once I will terminate this webinar, there will be a short survey with just about, I think, 5 questions. So it should take only a few minutes to fill out. Of course, we would appreciate very much if you would give us a little bit of feedback in that survey. So again, goodbye, thanks for watching, and hope to see you soon.